Okay, I think I'm live. Yeah, I hope everybody out there is doing okay. I just thought I'd jump on to do like a quick kind of Q&A session for anybody who's preparing for their A-level physics paper 2 exams tomorrow. So it's been great to have so many people here for the weekend. I've been doing masterclasses online. I did one today for AQA, I did one yesterday for OCR, and then last weekend and in the week I've done some others for Edexcel and other things like that. So yeah, basically I'm just here at the moment. If you have any particular questions, I'll see what I can do. I suspect there might be a lot of people watching at times, so I can't promise to answer everything, but I would like you to have a look at some things I've already pre-prepared on my website that might be useful later on. Did I do the questions and the proof from this morning? Says Man. Yeah, so basically this morning there was an equation that we were looking at how the EMF is equal to BAN omega sine omega t. I sent an email out to everybody this morning kind of showing this, and I basically used a bit of ChatGPT just to kind of double check that what I was doing was okay. But basically, if we've got a graph where we've got something that maybe looks a bit like this, okay, and we've got maybe time along the bottom axis, and here we've got the flux linked, so that's n phi, we can see that this is changing with time. Now, if we were to say that n phi is equal to cos omega t, okay, and I guess let me just get the equation sheet. Sorry, it's BAN cos omega t. And by the way, this is, for anybody who's now stressing, this comes up in AQA, it's not in OCR or Edexcel. Then basically, if we want to look at the total magnetic flux linked, it's equal to BAN cos omega t, where basically the angle that it's kind of rotated through is going to be equal to omega t, okay? And this is, for example, imagine you have a very simple kind of generator where we've got just maybe like the poles of a north and a south magnet. We've got a coil which is rotated within that. Now, the EMF is going to be equal, and I'm just using, I'll put a curly E to show the EMF. The EMF is going to be equal to N d phi by dt. So it's basically the rate of change at which N phi is changing. And therefore, if we want to look at the rate of change of this, that's just going to be equal to BAN cos omega t, and then we're going to differentiate that with respect to time. Now, of course, there's also going to be a negative symbol in here, because this bit here in blue is to do with Faraday's law and the fact that the rate of change of flux linkage is proportional to the EMF. And then we've got a negative sign here, which is due to Lenz's law. Now, if you basically look at this, so let's say we've got d BAN cos omega t, we differentiate that with respect to time. We then have the bit in front that stays the same, so that's BAN, and then the cos is going to become a minus sign, and because we've got omega t, we bring the omega in front of that, and then we still have omega t. Okay, so basically that's what happens. So of course the EMF then is going to be the negative of this, and because we've got a negative symbol there, that means the EMF is going to be the positive value of BAN omega sine omega t. Okay, so that's kind of what I did earlier on. So for those of you who were in the masterclass, I did send out a document with this in it as well. Right, why does the AQA equation sheet not have the minus? So my understanding is that in the AQA specification, it says that the magnitude, take your top off if you love physics. I don't know if me taking my top off for a load of children is going to kind of add to my longevity on YouTube. So I'm afraid I'm not going to take the top off. But yeah, thank you so much, Oscar, for the donation. I'm going to like that. There we go. 7 likes already. Give it a heart. Okay, do you know what? I'm going to put that up in the... I'm going to see if I can pin that. Can I pin that comment? I don't know if I can pin that comment, but thank you so much, Oscar. Yeah, basically the AQA specification says that the magnitude of the EMF is equal to the rate of change of flux linkage, which is basically Faraday's law. But I think sometimes having the negative symbol there is important as well. I think it really depends on, I guess on the kind of question you're asked about. Okay, somebody says they're 18. Yeah, okay, whatever. Right, somebody says they're so cooked. Look, you've got, basically, if you don't know it now, you're not going to know it. And you've had years and years of doing A-level physics and you're going to be absolutely fine. Right. Do I think there will be a question? So this is Luca says, do I think there will be a question on dielectrics in capacitors tomorrow? I reckon I've no idea. Nobody knows what's coming up apart from the small select group of people who love making children's lives hell. The people writing the questions, they know what's come up. But potentially there could be a question about a dielectric, but I would say that's going to be only 1 or 2 marks, and it's very much an explain the effect of that. So I don't think it's a big deal. So somebody says, incognito, if AQA drop another impossible paper, I might actually lose it. I'm sure it's going to be fine. Paper 1 was fine. There's no reason for paper 2 to be anywhere near as bad as last year. And the fact, and actually, after I did my masterclass this morning, somebody asked me a question. I answered the question, but I used the revised paper 2 from the AQA from 2024, which is actually different to the one that was initially put out. Now, the fact that the exam board had to revise their exam paper because the first one was just too difficult shows that they know there's been a problem, and I'm sure they've scrutinised the AQA paper 2 a lot more. Tips for multiple choice questions. I would say, if you know your physics, they're going to be fine. That's all it is. Basically, don't forget if you're doing a multiple choice question that you can still draw a diagram to help explain it to yourself so you can visualize what's going on. I'd then say if it's a numerical one, I probably wouldn't even look at what the options might be. I'd just do a normal kind of approach of writing down the equation, showing you're working out to find the numerical answer, and then see if that's one of the answers that they give you. Apart from that, if you're not sure, leave it and move on, and don't spend more than 2 minutes doing that multiple choice question. Okay, right, okay, let's have a look. Somebody says, yeah, right, okay. Can I explain how a step-up transformer works? And do you need to know it fully for AQA? Says not sure. Yes, you need to understand about how transformers work. And basically a lot of that is exactly the same as what you might have done at GCSE if you did triple science. Because basically it's incorporating lots of parts of the A-level course that you know. So you know, for example, that if you have a coil of wire, when you've got a current that's going through this, there's going to be an associated magnetic field. Okay, so let's imagine the current is going around maybe that direction. In this case, when the current is going this way, there'd be a north end at the bottom and a south end at the top. So we've got a solenoid here, which is just a coil that can carry a current. And of course, when the current goes in the other direction, I'm going to put that in green. When the current is going in the other direction, that field direction changes. So what we then have is we have a magnetic field that's going to be changing. Okay, and when you've got a magnetic field which is changing, there's going to be a change in the magnetic flux density that also depends on the number of turns. And that means there's going to be an EMF induced in other things which also experience this changing magnetic field. Now what we can do is we can basically channel those magnetic field lines through the iron core, which is magnetically soft, so it becomes magnetized and demagnetized easily. And basically this means that the field lines, rather than just kind of going out into all directions in the air, they're basically channeled around here. And so now we have an alternating magnetic field, and if that goes through a secondary coil, we're now going to induce an EMF, and if this is part of a complete circuit, this induced EMF means that we then have a current. Okay, and basically that's it. So what we have is the fact we've got a magnetic field next to a current, and then of course what we have over here is we then have an induced EMF. And basically, break it down step by step, what happens at each different stage. But to be honest, you don't need to go into any more detail than you already learnt at GCSE. What equations should you know that aren't on the equation sheet? There's not a huge number, to be honest. Do I eat, sleep physics? Yeah, basically, I feel at the moment I'm doing more physics work than lots of people watching this, because I'm not getting distracted by doing A-level maths exams or A-level chemistry or economics. I'm basically just living. It feels like every day at the moment I've been working on physics stuff, which I really enjoy. But I reckon because I've just done so many past paper questions over the last year, because I've done them for OCR, Edexcel and AQA, I've done so many past paper questions and I've explained them so many times to so many people, that is definitely the way that I've just got probably even better now at teaching A-level physics than when I was a teacher. Right. Yeah, I don't think, to be honest, I don't think there's too many equations that they don't give you. Okay, somebody says, yeah. Right, so let's see what people are saying. Okay, so Kieran says you ran out of time on paper one, had to guess lots of multiple choice questions. Oh, here we go. Bison Maths is here as well, everybody. So Bison Maths in the chat at the moment. I know he's doing great things. Yeah, and also, yeah, good luck to everybody in the exam tomorrow. I suspect most of you, if you're here today, then also you'll be kind of quite familiar with a lot of Bison Maths videos for A-level physics, especially those of you doing further maths. Great to hear from you. It's great to have you here. You know, Z Physics might turn up. Science Shorts never turns up. He doesn't speak to me. There we go. Right. So, how do you stop running out of time? I just think that the way to stop running out of time is just to not feel that you have to answer all of question 1 before you go to question 2 and then do all of question 2 before you go to question 3. I think it's probably better to do like a bit of question 1, get the easy marks, and then go on to question 2, get the easy marks on question 2, then get the easy marks on question 3. And that means you maybe feel like you're kind of spreading yourself a bit thin, but at least you've had a go at each question. You know what's coming up, and that means you're not going to completely miss out a whole question, where often the first couple of parts of that question are the kind of easy marks, where you're often stating things, putting down definitions, deriving things, and they're the things that you want to get that kind of the good base of marks to then spend your time later on looking at the slightly more challenging questions that take you a bit longer to do. Okay, so somebody says that Science Shorts denies climate change. Yeah, okay. Okay, so somebody says they want some official merch with the Physics Online t-shirt. I've only got, I think, 4 or 5 of these now, so I just kind of wear them in a loop. But to be honest, I don't know what kind of 17, 18-year-old students actually would wear a Physics Online t-shirt. It's just one of the things that I don't think there's like the kind of merch that I can really sell. I don't know if I've got quite enough numbers of people to actually kind of make merch. Who knows? We'll see what happens in the future. Okay. Right. What do I think the grade boundaries will be for AQA? Ignore that. You don't need to worry about grade boundaries, because basically you've got no way of knowing what mark you actually get. So obviously everybody's trying to get everything correct, but there's no point trying to second guess what mark you got and therefore what grade boundary it is. The main thing, and this is what AQA said when I spoke to one of their science advisors the other year, he said the main thing to concentrate on is just to get as many correct answers as possible. You do that, that's all that you can do, and then let the grade boundaries be worked out by somebody else. Right, okay. Oh God, there's so many questions here. Right, okay, so there's so many questions. Somebody's going to get a Physics Online tramp stamp. I would love to see that. If somebody gets a tattoo of my logo, I'll be well impressed. Do I have any predictions? No, there's no predictions at all. I've got no idea what comes up or what doesn't come up. What I have noticed, though, is that in previous years, there have been similar questions from maybe 2022 to 2023, or a similar question from 2023 to 2024. So just because it came up in 2024 doesn't mean that a similar question won't come up again. So you can't make predictions about what might come up. It is pretty much impossible to predict the topics and the style of questions. So basically, just do as many things as possible. Somebody then is talking about electric potential. Okay, let's look at that. So the potential, I think they're thinking about maybe gravitational potential. So gravitational potential is going to be equal to Gm over R, whereas if we're looking, so I'm just going to put a G there, whereas the electric potential is 1 over 4 pi epsilon naught Q over R. Okay, and both of these have a negative sign. Okay, so basically the potential is going to be a negative value, and this is going to be the gravitational potential per unit mass or the electric potential per unit charge. What we want to do though is, if sometimes it might be more important to actually think about maybe the energy or maybe the change in energy as something moves from one point in a field to another, and then rather than looking at this, we'd be basically saying that the change in gravitational potential energy would be equal to Gm over R times the mass which is moved. And often when you've got a question, we tend to look at maybe something going from one point to another, and therefore it might be more important to look at the change in gravitational potential, which would be equal to Gm over R, sorry, Gmm by 1 over R1 minus 1 over R2. So this would be if we're looking at the change in gravitational potential in a radial gravitational field as an object maybe moves between positions R1 and R2 in that field. Okay, we get the same thing when we look at the electric potential. This is going to be equal to not Gm, this is 1 over 4 pi epsilon naught times Q over R. Okay, and it doesn't matter if we talk about Q1 and Q2, big Q, little q. This is just looking at the sum of the two charges over the distance between them. Okay, and that's how we look at the gravitational potential at those points. Yeah, all right. Let me just check one thing about that. They tend to give you most of the equations that you need. Yeah, I think that they pretty much give you everything you need to know about this kind of topic, don't they? Yeah, right. Okay, so lots of questions. Do you think there's going to be much nuclear? Haven't seen much of it in past papers. Like someone says, nice goatee. Yeah, I just haven't shaved. I'll probably shave tonight because it's getting to that itchy stage. Some of you, when you're old enough, you might know what it's like to have a bit of facial hair. Right, so do I think there's going to be much nuclear? Probably. I think nuclear is quite a nice topic, and I think often the questions about nuclear physics, they tend to bring in aspects of exponential decay, which you'll see with things like capacitors. Potentially there could be stuff about momentum, maybe if you've got the collision of particles, or maybe things being emitted. There's also lots of links to real world things, especially if you're doing OCR, and the link between nuclear and medical physics and how things are diagnosed. Okay, yeah, right. So, yeah, basically, if there's anything that you want to see tonight that you haven't got an answer from me, because I know that I can't answer everybody's questions, can I just show you some stuff on the website, A-Level Physics Online, that might be useful to you? Basically, I've got lots of stuff to help you. So the first thing is from the main page. It says Past Paper Finder. If you go to the Past Paper Finder, what you can do is you can select your exam board, you can select the level, which would be A-level, and it's going to be paper 2. And then what you'll find are all of the past papers in an easy to find way. So let's have a look, maybe, so there's no copyright issues, let's look at some OCR stuff. There's basically the question paper you've already done, you've done the mark scheme. There are the examiner's reports here as well that I've linked to, so you can read up a bit more about the question and look at what how other students did. So for example, this question here, is about the half-life of fluorine. It says only around a third of the candidates were able to give the correct response of C. So this one over here, it just shows that if you got this wrong when you were doing your preparation, lots of other people got it wrong as well. So examiners report super useful. The best thing is though, I think here, if I just go to all exam boards and we've got paper 2, I'm just going to tick here to show that I've got work solutions for the AQA, Edexcel and OCR-A physics papers from 2022 and 2023. So if you need more help on a particular question, I do have work solutions. So you can find the work solutions here, where I actually go through every single question and kind of my kind of example approach. I also have, for those of you with a premium plan, or those of you who have school subscriptions, there's a video walkthrough where I actually go through the whole paper as well. So you can see here, I've got my video walkthrough. You can easily skip forward to the question you might need. Say, for example, it's question 14. You can click on that and then you can easily find my work solution to question 14 in that paper. And of course, that stuff there that you can find, and I've got the same stuff for paper 3. So I've got work solutions. If you've got paper 3A coming up in a week's time, I've got astro, medical, engineering, turning points. I've also got the Edexcel paper 3 and the OCR paper 3. So I've got work solutions and video solutions for all of that you can find on my website. The best thing, or one of the other good things I've done this year, is I've got the grade boundaries in one place. So here at the bottom of the page, you can see it says grade boundaries. If you click on AQA, for example, this has all of the AQA grade boundaries in one place. So you can see, for example, that with AQA, what they did, they had quite easy papers up until about 3 years ago, where suddenly they must have got some people on the team who just don't like children, and you can see that the kind of grade for an A star went from about 65 down to about 54. And even last year, to get a grade A, you needed to get 41 marks out of 85 to actually get a grade A on that paper, which just meant the AQA paper 2 last year was just too hard. So there's loads of these kind of grade boundaries there, and of course I do have these actually for all of the exam boards. So I've got them as well for even the 5 or 6 people who do OCRB, and there's I think 4 or 5 people in the country who tend to do EDUCAS. So even if you are one of the few EDUCAS people out there, I do have the grade boundaries here as well. So you can look at electricity in the universe. You can see the grade boundaries here, which tend to show that actually the EDUCAS papers are a bit nicer than some of the AQA ones. So I've got lots of stuff there to help you. I also have lots of videos. So if you go to AQA, if there's anything that you're not sure about, maybe with nuclear physics, I've got videos here. You can find them sort of by topic. So anything you're not so sure about, you can find videos here that can be useful. So there we go, the alpha scattering experiment, how to derive closest approach. Lots of good stuff on the website that you can use in the middle of the night tonight as you're having that panic attack because you're maybe not sure about how to actually approach a question. Okay, right, so let's see what other people are saying. Yeah, I'm trying to sell my course because that's basically why I'm here, and that's why I'm here on a Sunday night in this studio doing stuff, because I just want to sort of show what's out there. And by the way, lots and lots of it is completely free. So all of my work solutions to download for all of the exam papers are all completely for free. Right. And yeah, I don't think AQA is going to be as hard as 2024. Do you need to know all the required practicals? I mean, you know them already at the moment because you did them. So you know the required practicals, if that's looking at maybe the force on a wire in a magnetic field, if it's looking at magnetic flux. All of this stuff is stuff that you already know, but it might be worth just spending 5 minutes just reminding yourself about the required practicals, because there could potentially be a question. Again, who knows what's going to come up in the exam, but there could be a small question about that, but really I've got no idea. Okay, can I go, right, sorry, there's lots of people's stuff here. Okay, how about what I'll do then in the chat is, let's see, what's the best way of doing this? I think Yeah. What I probably should do is only have people who are subscribed in the chat, but I think I probably can't do that while the chat is ongoing, can I? Because there's a lot here. Okay. Right. How do I turn on slow mode? God, this is like me being really... Okay, so let's try that. No, let me... This is where I need to get somebody else, a moderator. Okay, right. Oh, is it already subscribers only? Oh yeah, of course. That just showed there's so many people. I think I'm almost at the 200,000, so I've only got like about 1,500 people to go. So, right, velocity selector. Shall I do that? Right. Okay, there's lots of stuff here. Okay, how about I'll do a velocity selector, because that's something that I've noticed in some of the masterclasses people find a bit difficult. So I'm not going to read the chat there. So I know there's people, by the way, wanting to be moderators, but yeah, right, a velocity selector. Right, this is an example of where you have a force due to the electric field, and you've also got a force. Okay, I really hope this comes up tomorrow. How many marks do I think there will be on definitions? I reckon definitions in total tend not to be that many marks in the exam. I think most of the marks tend to be about applying your knowledge rather than just rote learning definitions. So if you don't know it now, unless you've got them at hand and can just do a quick flashcard, a reminder, I wouldn't spend like 3 hours just doing definitions, because they're not going to be that many marks, and they're very much the easier marks that you get rather than the kind of the higher marks that kind of get you to the higher grades. So I think definitions aren't going to be a big part of the exam. Okay, basically there are two forces that we can think about. There's a force on a particle moving in a magnetic field, moving in an electric field. So let's imagine we've got an electric field. We've maybe got a positive plate, and this one's at 0 volts. And if we put a particle here that's moving in this direction, if that particle has a charge, let's imagine it is negative. So this is a negative particle. It's going to experience a force due to this positive plate, and the force is going to be upwards. Okay, so this is going to be the force due to the electric field, and that force is going to be equal to EQ. Okay, it depends on the electric field strength and the charge on that particle. And also, the electric field strength, sometimes it's not given to you, but this is equal to V over D. Okay, it's equal to the potential difference divided by the distance between the plates. So this is a force due to the electric field. And then there's also going to be a force down if we've got a magnetic field acting on this particle as well. Now, if you've got a magnetic field which is going into the paper, we can use Fleming's left-hand rule to work out the direction of the force. Now, if it's a negative particle going to the right, that's the same as conventional current going to the left. So I'm going to use my left hand and put this finger pointing to the left. I'm going to have my first finger pointing down, because that's the direction of the magnetic field, and my thumb points in the direction of the force. And that force is due to the magnetic field. So now we've got a particle moving through a region where we have an electric field which is going up and down, and perpendicular to that, going into the page, we've got this magnetic field. Okay, and that means this force here is going to be equal to BQV. It depends on the charge on the particle, how quickly it's moving, and the size of that magnetic field. Now, if something has equal forces on it, up and down, it's going to keep going on in a straight line, and therefore the velocity is going to remain the same. And that's when the force due to the electric field is equal to the force due to the magnetic field. And therefore what we can say is that EQ is equal to BQV. And then we can see that the Q's cancel, and then we can rearrange this to say V is equal to E over B. Now, this is something that basically incorporates your knowledge of electric fields and your knowledge of magnetic fields. And this thing here is called a velocity selector. And what it means is that particles that travel at the same velocity will move through the whole thing and they'll come out the other end. If a particle is moving quicker than this certain v that we want, if it's moving quicker, then that means the force due to the magnetic field is going to be bigger, and that means it's going to move down. So the particles with a high velocity move down. If they're moving quite slowly, the force due to the magnetic field is going to be smaller, and they're going to move up. So that's for low velocity particles. And what this means is if you have a velocity selector, we can look at a whole range of particles, maybe ions, and all the ones that come out the other side must all be travelling at the same value of velocity. And this is used in a mass spectrometer, because in a mass spectrometer you have this velocity selector, and then the particles come out at the same velocity before they go into another region where we maybe have a magnetic field. So here we have another magnetic field, maybe going into the paper. There's still going to be a force down, but now the particles will travel with a circular path until they get to the other end. Now here, if they're moving with a circular path, the force is equal to BQV, and that's going to be providing a centripetal force on them, which is equal to mv squared over r. And if we equate these two things together, we can see that a v cancels, and then r is equal to mv over bq. Now, if all the particles in here are travelling at the same velocity, they're all in the same magnetic field and they all have the same charge, that means the radius is proportional to the mass. So heavier particles have a bigger radius of curvature, and so you might find that light particles do this, and then heavy particles do this, so maybe that's a small m, and that's a bigger m. And what we can then do is maybe have a load of ionised ions, or ionised isotopes. They've all got a charge, but the isotopes might have a different mass. And we can look at the difference in the kind of relative abundance of different types of isotope. So that's an example of using a velocity selector before a magnetic field for particles in maybe a mass spectrometer. There's lots of kind of good physics that this involves. Okay, right, so, okay. If the charge is negated, why does the electric or magnetic field need to be changed? Will it still work? Okay, so basically, although we cancel it in the equation, we only have this force arising if the particle has a charge. If it was a particle moving at a velocity, there wouldn't be a magnetic force acting on it, and therefore FB would just be equal to 0. Okay, and so would FE. So basically, if there's no charge, it wouldn't be deflected at all. It would just keep moving at whatever direction it was initially moving in if there wasn't a charge on that particle. Okay, right. Why does it move downwards if it's going fast again? Yeah, so basically, because this force here, the force due to the magnetic field, is equal to BQV. Now imagine you had something going twice as fast, and it had the same charge. If it was going twice as fast, then the force downwards would be twice as big, and therefore the force down would be bigger than the force up. So basically, if they go a bit too fast, they go down. If they go a bit too slow, they go up. And just like Goldilocks with her porridge, if it's just right, it kind of keeps going straight through the middle. Okay, right, how's that helping? Right. Right, there's so many questions, sorry everybody, and by the way, lots of you have sort of questions on similar topics. Okay, I'll maybe finish, I'll probably finish at about 8:30, because by that point, basically, you're all good, by the way. Okay, binding energy, people love binding energy, don't they? Right, I'm going to do about another kind of 6 or 7 minutes. Binding energy, so you have a nucleon, you add it to another nucleon, and what you get isn't exactly double the mass. Okay, so imagine that had a mass of a kilogram, that had a mass of a kilogram, you add the two things together and it's like 1.999 kilograms. So what we find is there's a mass defect. Okay, there's going to be a change in mass when things bind together. Okay, that is just like, ignore the numbers, these are just kind of made up. Now, basically, there's going to be a mass defect, which is the change in mass. And the way I think about it is, if you want to separate these two things, which if they're nucleons, inside the nucleus, there's this strong force of attraction. So the strong force looks a bit like this. Okay, sort of at about less than 3 femtometers, it's negative, so it's going to be attractive. And these two things, in order to separate them, you need to add energy. Now, when you add energy to them, so maybe we're adding some energy externally, that adds to their mass. So as you pull them apart, because we have to apply, or we have to add energy to that, that's why the mass increases. And this goes back to E equals mc squared. Okay, if you're adding energy to something, that means the mass of it is going to increase. Now that means, of course, when they come together, some of the mass has now gone back into energy. And we release energy when things like this bind together. And what's more important sometimes than the binding energy is the binding energy per nucleon. And what we find is it kind of gets up to a peak and then it kind of drops away. This is round about iron at the kind of top. And basically, if you've got smaller things, when you join them together, there's going to be more binding energy per nucleon. And that means energy is released when small things join together and they fuse together, and until we get to kind of things around about iron. If you've got really heavy things, as they split apart, because there's going to be more binding energy per nucleon in the products compared to the reactant, which might be something like uranium, there's going to be more binding energy per nucleon for the same number of nucleons, and therefore there's going to be a greater total binding energy in the daughter products of maybe something which is split apart. Okay, so yeah, and of course the binding energy is the energy required to separate the nucleus into its constituent nucleons. And if we know the size of the binding energy, we can then use E equals mc squared to look at the mass defect, or vice versa. Okay, yeah, but I think this graph here is super important. Sometimes they give you numbers, and if you knew the nucleon number and you knew the binding energy per nucleon, you could look at then the total binding energy of that nucleus. Okay, hopefully that's a kind of a brief thing about binding energy. I know it's difficult because there's so many things to say. I do have videos that I cover all of this, but I'm hoping that's a bit of a reminder, really. Right. Right. Okay, sorry. Can you look at electron diffraction to find... No, hold on. So if a nucleus binds together, it basically gives out energy, and that means you have to add energy to the nucleus to actually split it apart. Okay, if you just started with all the individual bits. Okay, but so if you had all of the individual protons and neutrons, and these all kind of joined together in one go, then they'd be giving out energy. So if you wanted to separate that nucleus into all the individual bits, you'd have to add energy to actually separate it. What do you need to know about eddy currents? Not much, to be honest. Eddy currents, you don't need to really know much more than kind of GCSE. Basically, if you've got a big block of metal and you've got a magnetic field around it, so you've got a changing magnetic field, every time you have that changing magnetic field, this is going to induce an EMF. And if you've got an EMF over a big surface area of a conductor, this will mean that we can get really big currents flowing. So we know, of course, that V equals IR. If you've got a very small resistance, because we've got a metal with a large area, and you've got a certain value potential difference, we can get really big currents. And these currents can basically follow the path of least resistance and sort of flow through that material. Now that means we now have a current, and therefore a heating effect, and therefore some of the energy is going to be dissipated in the core. So what we do is we basically split up the metallic iron core with insulating strips, And this just means that if an eddy current starts to form, it doesn't have the freedom of movement to just move anywhere. It kind of gets stopped by the kind of the different parts here. And so by having a laminated core, we just reduce the distance that these currents can actually flow through, and that means we make a much more efficient transformer. Okay, and right. Do you want a high resistivity for a wire or a low resistivity? Depends what the wire is for, but normally if you've got a low resistivity, we have a low resistance, which is what we want in a circuit. Okay, right. Somebody says they hate to say it, but they think they're going to miss this channel. Yeah, alternating current. Okay, alternating current, that's not a big deal, to be honest. Alternating current, they often give you quite easy questions. If you've got an alternating current, then if we were to look at maybe the potential difference or the current, the average value, because sometimes it's positive and sometimes it's negative, the average value, if you were adding up all of the different values, would be equal to 0, which doesn't really tell us much. Okay, so that's like saying that the average voltage from the plugs in the UK is 0, because sometimes it's positive, sometimes it's negative. What's more important to do is actually look at this data, and what you want to do is when there's a negative thing, okay, all digging the beard, Time Lord, thank you so much, keep up the good work, thank you very much, appreciate the donation, that's awesome, thank you. Yeah, so basically, rather than looking at V, when it's positive and negative, we want to maybe look at the square of all the values. So if we were to look at V squared, when that's 0, V squared is 0, but these values here are just going to be much bigger. And when the values are negative, because we're squaring a negative number, we get a positive number, and then we've got a positive thing like this. And then what it might be more useful then to look at is the average of the square of the number. And if you did that, we then find that effectively the average is going to be like this. But that's going to be the average of the square. So that's the average of V squared. But what we can then do is we can square root it to kind of basically bring it back to kind of like the normal scale that we had up here. And so what we then get is a line a bit like this, where this is the square root of the mean value of the numbers squared, which is why it's a root mean square. So it's the square root of the mean of the square of all the numbers. And effectively that would then have the same effect as if we had a DC current. So what that means is if you had something where the peak value went up to, I think, plus 268 volts AC, that would be equivalent, it would have the same heating effect as maybe a direct voltage of about 230 volts or something like that. Okay, so basically the root mean square value is the equivalent DC supply that would have the same power or heating effect as that. Okay, right. Yeah, I think basically by this point, all of you, you're going to be fine. Okay, it's been amazing to have so many people here. I will be here again during the week. I'm going to do some maybe paper 3A master live streams. I'm going to be doing a masterclass next weekend, Sunday morning. I've only got limited spaces. I'm only going to be doing one masterclass for paper 3A, so that's Sunday morning. But yeah, basically, I'm going to be finishing up there. I think there's a lot of stuff here that it's important to just realise that you know all of this already, okay? Don't get fixated on maybe one or two past paper questions which weren't very good in the kind of maybe past paper you've had a look at. For example, if you found that there was an AQA paper 2 question that you found difficult from 2024, just ignore it because it's very unlikely they're going to ask you the same thing, and just concentrate on the other 90-95% of questions that you've been absolutely fine with. Go into the exam tomorrow, just make sure that you don't run out of time by not getting fixated on difficult questions. There are going to be lots and lots of easy questions throughout the whole exam. There will be definitions that you can just write down. There might be a derivation that you've done many times. There might be questions that are so similar to other things you've done. And I'm sure by the time you come out at 11 o'clock in the morning, half 11, it's all going to be fine. And then for most of you, you're going to be, you know, well over halfway through your whole exam period. Yeah. Somebody says PMT is saving me. Really? Come on. You're talking to me. Although, by the way, I've done loads of stuff on PMT. I did lots of work solutions to their multiple choice questions for AQA and so on. Right. But yeah, apart from that, just get to bed, get some sleep. If you don't know it now, you're not going to know it by the morning. So you may as well just get to bed. All right. Okay, PMT is actually the GOAT, so somebody else. Okay, well, anyway, I've got more work to do to kind of catch up with PMT and make something better than what they've got. Right then, thanks so much, everybody, and I'm going to leave it there, and good night. Oh.